Hey, this is Dr. B, and let's talk about formal charge and resonance. And let's do it by just picking some examples. Imagine you wanted to draw something like carbon dioxide. Well, we recognize that carbon has 4 valence electrons, tends to form 4 bonds, no lone pairs. Oxygen has 6 valence electrons, tends to form 2 bonds and have 2 lone pairs. Always draw the substance that forms the most number of bonds first. That's carbon, and let's give it an oxygen and an oxygen, but it forms 4 bonds. That's good, and I like the fact that oxygen has 2. We'll throw the lone pairs on there. And wonderful, we have a very reasonable structure there. Some aren't so reasonable. Carbon monoxide exists, for example. But it's not going to play according to the rules that we have. I mean, I could try this. And I do like oxygen. 2 bonds, 2 lone pairs. I do not like carbon. It's short a bunch of things. It's short 2 bonds. And if we try to evaluate this, or we consider the formal charge on it, meaning the charge it would have if it were ionic, meaning that this would be worth 1 each. I count 1, 2, 3, 4, 5, 6. No charge. Nice. Notice also that it has a full octet, which is very important. 2, 4, 6, 8. Here we're counting those shared electrons in the molecule. No charge, full octet. Yay! This carbon's not so good though, is it? It has only 2 electrons and it needs 4. Since electrons are negatively charged, we're short 2, so this has a +2 formal charge. Meaning if it were ionic, which it's not, but that's how we evaluate it. It's our best attempt to give these things charges. And it definitely only has 4 electrons in terms of an octet, the ones that it shares. So no octet. If you played around with it and tried to draw it a more reasonable way, we could do something like this. Ooh, it certainly looks weird already, but let's make sure we have at least a full octet on everything. So I need 2 more electrons here. Why don't I go like that? 2, 4, 6, 8. Got it. So octet. Yay. And why don't I go 2, 4, 6, 8 there. Octet. Check. This is in fact the best way we can draw carbon monoxide, but now let's evaluate it for formal charge. If we don't overall get a formal charge of 0, it's certainly not reasonable, because carbon monoxide has no charge. So, counting each as 1, which is how we evaluate it, we get 1, 2, 3, 4, 5, but carbon's supposed to have 4. We're going to give this a formal charge of -1, 1 extra electron. Do the same thing for oxygen. Tell me what you get. You should get 1, 2, 3, 4, 5 there also, but it's supposed to have 6. It's short 1. This is +1. Overall, it's uncharged. And this is the best you will do to draw the structure of carbon monoxide. So that's a little look at formal charge. In terms of resonance, consider something like the nitrate anion. And I think we can see over here. If you do a similar kind of thing, you're not going to be able to draw it reasonably because it's supposed to be NO3-. Play around with it, and I'll bet about the best you'll be able to do is give everything a full octet. Ooh, good. A garden variety oxygen, 2 lone pairs, 2 bonds. But these 2, I need a full octet, so I only have 2. I got to add a whopping 6 electrons to each. But at least I have a full octet, right? 2, 4, 6, 8, 2, 4, 6, 8. And check out nitrogen. It's already got a full octet. If this thing comes out to be -1, I should be good. Evaluating them for formal charge, this is 0. 1, 2, 3, 4, 5, 6, yay. This one has 7. 2, 4, 6, 7. That's -1. So this one must also be -1 because it's identical. And this one only has 1, 2, 3, 4. It's short 1. Overall, I like it because we have -2 plus 1. It's -1. So this is the nitrate anion. But now we run into a different problem. if you actually evaluate this thing spectroscopically and otherwise, you find that all the bond lengths are the same. This would predict we have a nice short bond length, very strong, and this is long and long. That's not what's observed in nature, and this confounded scientists for years. They need to come up with some way to at least represent it that's reasonable. So the obvious answer, at least to me, would be that it's not a double, single, single. It's like 1 1/3 each. Each one has, oh, I don't know, you could try to draw it like this. Let me draw it down here so you can see it. Something like that. That might be okay, right? And I guess 2 lone pairs, there, and we should even have, I guess, a lone pair there, but they're not. It's messy, isn't it? It's like partial, and they didn't do that. What they did instead is say, why don't we tell everybody it's the average of 3 different structures. Now watch what I'm going to do. I'm going to shift this a little bit over. And they said, this is the average of this, where I'm going to shift things around, use double-headed arrows, and draw it like that. Exactly the result. Take those 2 pairs of electrons, put it there, and in other words, the double bond is evenly distributed between the 2. These arrows, I hope, make some sort of sense to you. Plus, minus, minus. And the last one, I'm going to put it down here. I hope you can see it. Double-headed arrows means it's just an average of these structures, and they're all pretty much the same, aren't they? Now I'm going to get that double bond over here by swinging it down. Oh, wrong way. Yeah, no, this is reasonable, but I want to get the double bond. I had it on the left. I had it on the top. I had it on the left. Now I want to get it on the right. There it is. So I'll go like this and like this. See that? That should put it on the right. And so there it is there. Since it's the average of these structures, we call these resonance structures, and it agrees with reality. It's kind of a pain that you have to draw 3 different structures in order to represent one substance, but these are the 3 resonance structures for the nitrate anion, and they're all considered equivalent. Formal charge and resonance.